Chapter 17 of Astronomy, the Science of the Heavenly Bodies, by David Todd. Chapter 17, Bradley and Aberration. Living at Kew in London early in the 18th century was an enthusiastic young astronomer, James Bradley. He is famous chiefly for his accurate observations of star places, which have been invaluable to astronomers of later epochs in ascertaining the proper motion of stars. The latitude of Bradley's house in Kew was very nearly the same as the declination of the bright star Gamma Draconis, so that it passed through his zenith once every day. Bradley had a zenith sector, and with this he observed with the greatest care the zenith distance of Gamma Draconis at every possible opportunity. This he did by pointing the telescope on the star and then recording the small angle of its inclination to a fine plumb line. So accurate were his measures that he was probably certain of the star's position to the nearest second of arc. What he hoped to find was the star's motion round a very slight orbit once each year, and due to the Earth's motion in its orbit around the Sun. In other words, he sought to find the star's parallax if it turned out to be a measurable quantity. It is just as well now that his method of observation proved insufficiently delicate to reveal the parallax of Gamma Draconis, but his assiduity in observations led him to an unexpected discovery of greater moment at that time. What he really found was that the star had a regular annual orbit, but wholly different from what he expected and very much larger in amount. This result was most puzzling to Bradley. The law of relative motion would require that the star's motion in its expected orbit should be opposite to that of the Earth in its annual orbit, instead of which the star was all the time at right angles to the Earth's motion. Bradley was a frequent traveller by boat on the Thames, and the apparent change in the direction of the wind when the boat was in motion is said to have suggested to him what caused the displacement of Gamma Draconis. The progressive motion of light had been roughly ascertained by Reaumur. Let that be the velocity of the wind. And the Earth's motion in its orbit around the Sun, let that be the speed of the boat. Then, as the wind, to an observer on the moving boat, always seems to come from a point in advance of the point it actually proceeds from, to an observer at rest, so the star should be constantly thrown forward by an angle given by the relation of the velocity of light to the speed of the Earth in its orbital revolution around the Sun. The apparent places of all stars are affected in this manner, and this displacement is called the aberration of light. Astronomers since Bradley's discovery of aberration in 1726 have devoted a great deal of attention to this astronomical constant, as it is called, and the arc value of it is very nearly 20.5 seconds. This means that light travels more than 10,000 times as fast as the Earth in its orbit, 186,330 miles per second as against the Earth's 18.5 miles per second. And we can ascertain the Sun's distance by aberration also because the exact values of the velocity of light and of the constant of aberration when properly combined give the exact orbital speed of the Earth, and this furnishes, directly by geometry, the radius of the Earth's orbit, that is, the distance of the Sun. In fact, this is one of the more accurate modern methods of ascertaining the distance of the Sun. As early as 1880, it enabled the writer to calculate the Sun's parallax equal to 8.8 seconds, a value absolutely identical with that adopted by the Paris Conference of 1896 and now universally accepted as the standard. In whatever part of the sky we observe, every star is affected by aberration. At the poles of the ecliptic, 23.5 degrees from the Earth's poles, the annual aberration orbits of the stars are very small circles, 41 seconds in diameter. Toward the ecliptic, The aberration orbits become more and more oval, ellipses in fact of greater and greater eccentricity, but with their major axes all of the same length, until we reach the ecliptic itself, and then the ellipse is flattened into a straight line, 41 seconds in length, in which the star travels forth and back once a year. Exact correspondence of the aberration ellipses of the stars with the annual motion of the Earth round the Sun affords indisputable proof of this motion, and as every star partakes of the movement, this proof of our motion round the Sun becomes many millionfold. Indeed, if we were to push a little farther the refinement of our analysis of the effect of aberration on stellar positions, we could prove also the rotation of the Earth on its axis, because that motion is swift enough to bear an appreciable ratio to the velocity of light. Diurnal aberration is the term applied to this slight effect, and, as every star partakes of it, demonstration of the Earth's turning round on its axis becomes many millionfold also. End of chapter 17.